previous exams from this course. So the type of problems that could appear on the exam, not comprehensive every type of problem that might appear on the exam, but it will give you some idea. So I'll hand it over to Elaine.
Thank you. Start. So the first problem is an MAP estimation problem. You have probably seen this in one of your homework, but again, it's a good memory refresher about the general steps for calculating MAP, and then you can take 1 or 2 minutes to think about this. And then it's also good practice if you can do some calculations on paper.
Look, the way they're doing here is just like they just added some padding. They just added a little bit of padding. Right, this is just essentially a little padding.
And you don't have to copy the question because I think this is from homework 6. Okay, let's go through it together. So first, the fundamental difference between MAP estimation and MLE estimation is that MAP comes from a Bayesian point of view. So most of the statistics probability theories we dealt with are from the frequentist view, where you have a fixed parameter theta, and then the random variable, let's say y, is drawn from a distribution that's parameterized by theta. So that's theta is fixed.
I can't really see the paper.
Oh. Do you have any idea how?
Where is it on this one?
Great.
There we go. Okay. So this is fixed. Theta is fixed. And this is the frequentist point of view. You might not hear the word frequentist a lot, but this is the traditional probability theory setting. But in MAP, we're using the Bayesian point of view, where theta is a random variable itself. So as in this question, we have a prior distribution for theta that captures our belief what theta could be. So theta comes from a prior distribution with a PDF function f theta equals 2 theta for theta between 0 and 1. And then after knowing more about the theta, we draw our random variable y condition on theta. So this is drawn from an exponential distribution parameterized by 3 theta. So the PDF is just lambda where lambda is 3 theta here. Okay. So for MAP, the probability we're trying to maximize is the posterior probability, the probability of seeing, probability of theta given the observation y. And this is proportional, by Bayes' rule, this is proportional to probability of y given theta times probability of theta. Are we clear with this step? Because you just apply the Bayes' rule. It would be equivalent if we put a denominator, divide this entire term by a probability of y. But again, we're concerned about theta here. So we kind of So that would be 3 theta times e minus 3 theta times 2 over 3. That's the y value here. And then 2 theta for the PDF, from the PDF of theta. That solves to theta squared e to the power of minus 2 theta. Okay, and then that is from a gamma distribution parameterized by alpha equals 3 and beta equals 2. So just like, just recall the definition of conjugate prior. Here, gamma distribution are conjugate priors for exponential distributions. And then, to find the value of theta that maximizes this posterior distribution probability, it's equivalent to finding the mode in the gamma distribution. If you have a formula sheet put out in front of you, you can just plug it in. So the mode of a gamma distribution is alpha minus 1 over beta, which is 2 over 2. That gives the result of 1 here. Any questions? So you want to pick a value of theta that maximizes this value, right? So you can write the rule, estimation rule here. So theta MAP would be the argmax of theta that maximizes this value here. And that just corresponds, let's say this is your distribution of theta given observation y. That corresponds to this point here. That's the mode. Yeah. Sorry, alpha equals 3 and beta equals 2. Well, this is comparing with the PDF of gamma distribution. So this is based on the assumption that you know that the gamma distribution is a conjugate prior for exponential distribution, so that the result we get is from some sort of gamma distribution. And then you compare this expression to the PDF function of common gamma distribution and pick out what alpha is and beta is. I think the general PDF would be something like theta to the power of alpha minus 1 and e to the power of negative beta theta. So that allows you to plug in and solve for alpha and beta. Yeah. Yeah, you could also do that. I think the plug-in method is most straightforward, but for a lot of distributions, calculating this using the standard differentiation method will also work. Okay. Next question, naive Bayes MLE. Well, this is more like an MLE setting, MLE question in the naive Bayes setting. So here we have a table of observations. We have 4 variables, random variables, or more feature, or we call it features x. So x1, x2, x3, x4, those are 4 variables. We also have another random variable y, which takes 3 possible values. And then the question is, what's the MLE for probability of any of those x I equals 1 given certain value of y? Can take half a minute to think about it. Okay. If you recall from lecture, the MLE from the naive Bayes problem for these kind of conditional probabilities can actually be calculated using simple counting method. Why this expression? Well, you can do it from scratch, using a standard procedure, writing the log likelihood of the data given this P, and then expand everything out, take the derivative and set it to 0, and then you'll get this expression. So this indicator function actually comes from the fact that we only care about cases when we see the specific feature xj. But anyways, the simple rule of thumb to remember is that for such cases, counting methods work for calculating MLE. So depending on different values of y, which y can take values +1, 0, -1, and then we have different probabilities for each of these for Bernoulli random variables being 1. Okay, so here, so this formula just basically means that the denominator is the number of times your y take this specific value, small y, and then the numerator means the number of times you observe that both your y takes this specific value y and your feature xj takes the value of 1. So referring back to our table, let's first see the case when y equals +1. For x1, so we see it's x1 equals 1 only once, but total number of times y takes the value of 1 is 2. So in this cell, we just fill it in 1/2. So the same thing applies. For x2, it's 2/2, which is 1. For x3 and x4, it's the same thing as x1. And then applying the same rule, counting rule for y equals to 0, we have half and half for the first two x, and then 1, 1 for x3 and x4. And then for the last case, y equals -1. So it's 1/3 for x1, x2, and x3, and 2/3 for x4. Okay, any questions about this counting method? Okay, cool. Just a recap of the naive Bayes assumption. So why would we need this sort of conditional probability anyway? How does it fit into the bigger picture? So let's recall what we did in naive Bayes algorithms. Basically, this is a generative algorithm, so we want to model the joint probability of x and y. So like this x here incorporates x1 up until x4 in this case. And then by definition of conditional probability, this can be decomposed into P of y times P of all the x given y. And the naive Bayes assumption allows us to simplify the second term into a product of individual x given y. So these individual conditional probabilities are the ones we just calculated. And this term can be similarly calculated using a counting method. You just count number of times y takes certain value over total number of examples. And then knowing this joint distribution, our ultimate goal for prediction is to find the label that maximizes the posterior distribution. I'm sorry, not the posterior distribution, the conditional probability. Basically, given the observations of x, what's the probability of y? What's the value of y that maximizes this probability? And again, applying the definition, so this is equivalent to p, the joint probability divided by the marginal probability of x. Because this term here is constant regardless of what y values we take, so this constant can be safely ignored for the purpose of prediction. So so we can just say that this term is proportional to the joint probability, which can be calculated using the formula here. Any questions? Okay, great. Let's move on to the next problem, hidden Markov models. You can quickly try these out on paper. Yeah. Yeah, just treat it as a first order. Okay, so let's go over this question. First, I'm sure you all know what an HMM model looks like when drawn in graph. So you have a series of hidden states. That's y1, y2, y3. And then you also have a series of observations coming from those hidden states. Are we good with this diagram so far? Okay. Why do we call it a Bayesian network? So recall the definition of Bayesian network. So a Bayesian network is basically a DAG plus that satisfies the property that let's just denote all the variables inside a random Bayesian network to be x1 up until xj. Then in any Bayesian network, this joint probability can be broken down into the product of probability of each variable given all its parents. So that's the definition of Bayesian network. So using this definition here, let's decompose the HMM network. So in also this is Bayesian network. Okay. So basically, the joint distribution is over x1 through x3, y1 through y3. That would be, let's cover the hidden states first. So y1 does not have any parent, so we put probability of y1. And then y2 has one parent, y1. And then y3 has one parent, y2. And then for the x1 has one parent, y1. The same thing applies for other x's. So the joint probability can be factorized in this way. Yeah. Oh, DAG. Yeah. Oh, it's a directed acyclic or acyclic graph, meaning that directed meaning that you have arrows that specifically point out the direction. Acyclic meaning that there is no circle in the graph. Okay, let's recall the HMM assumption in first order Markov chain. So the first assumptions we had is the Markov assumption. So let's assume first order. The Markov assumption is saying that probability of yt given y1 up until yt minus 1 is equivalent to probability of yt given yt minus 1 itself. So it means that condition on the previous state, we can safely, so the current state is conditionally independent of all the previous states prior to the previous state. This property actually, you can clearly see this property from the Bayesian network point of view, because each hidden state, y, only has its previous state as its parent. So condition on this parent, it's essentially independent of all the previous states. So like y3 might be a better example here. So if we condition on its parent y2, it would definitely be conditionally independent of y1. Another important assumption we make about HMM is the output independence assumption, which states that probability of xt given all the hidden states, basically all the other variables. Sorry, let's use capital T to denote like the final state, and then x1 up until xt is equivalent to the probability of xt conditioning on yt. Meaning that conditioning on the current hidden state, the current observation is independent of every other probability, every other variable in the graph. So we can also check this assumption using the Bayesian network point of view. clearly only YT. YT is the only parent of XT. So again, I think there was a lot of confusion about assessing the independent statements assumptions in an HMM model. So I guess the most straightforward way is to treat it as a Bayesian network and determine the conditional independence assumptions using the definition of Bayesian network. Again, so just to emphasize again, Bayesian network assumes that the probability, not the probability, conditioning on, if we have a variable x, then conditioning on all of its parents, it is independent of all the other variables that are not its children or its descendants. Why do we exclude the children of x? Because if we're interested in, if we look here, ultimately we would have a term for P of, let's say, x child or children given x. And that essentially means that x and its children are not independent. So again, the assumption is only that conditioning on x's parents is independent of everything else that is not its descendants. Any questions? Yeah.
The formulation of the question hasn't been mentioned. What is the state or what is observation? Is that the general thing?
It's a standard model for HMM. So basically, you always have a series of hidden observations, hidden variables, and a series of observations like this.
So it is okay to assume that y is being referred to as a hidden state.
Oh, the notation might differ, but we'll make it explicit in any questions we show to you. Oh, okay. Great. Now I will hand over to Ryan.
Can you hear me? Good. Okay, so next we're going to go over k-means. So I'll give you about a minute to think about this one, and then we'll go over it. Okay. So in k-means, we have 2 steps that we go through at each iteration. So on step 1, we are going to first assign points to clusters based off of their distance from the cluster centers. And then in step 2, we will define new cluster centers based off of the points assigned to each cluster. So here, just looking at this left cluster center, we ask which points are closest to that cluster center compared to the other cluster. And that's this point, this point, this point, this point, and then this one. Are all close to this one. And then looking at the other cluster center, it's just these 3 points. So we've assigned clusters, or assigned points to cluster centers, and then we define new centers. And so we can, I guess, do this exactly. So we have 4 points that are all kind of around this one, and so we have one, the y coordinate will be 0.5, and then 4 points with an x coordinate of 0, and 1 with 1. So we have this point moves to here at 1/5 and 0, or 1/5 and 1/2. And then here, these are the 3 points assigned to the second cluster, and we take the mean of these 3 points and find that it's actually the same point. So this cluster center doesn't move. Okay, so now we go on to the next iteration and we ask what points now belong to these new cluster centers. And it turns out that the answer hasn't changed. The same points belong to the same cluster centers. And then if we were to recompute the cluster centers from those points, we'd get the same answer. So we know that we've converged. So this is the converged answer. Okay, so we've assigned, just to be clear, these points as one cluster, and then these points as another cluster.
What are the coordinates you mentioned for the
The first center is at 1/5 and 1/2. Oops. There you go. Sorry. Any other questions? Okay, we'll move on to the next question, which is another k-means. And again, I'll give you about a minute to work on this. Okay. All right, so this is very similar to the previous problem. It uses the same points. And so we can answer this question just by running one more iteration of k-means and seeing if the answer stays the same. So we start off by finding the cluster centers. So here's one cluster. The cluster center is right here. That would be at 0 and 1/2. And then the other cluster center is right here. Okay. So now we go on to the next iteration, or we complete this iteration and assign the points to new clusters, and we get this one, this one, this one, this one, and this one now belonging to this first cluster. And then this one, and this one belonging to this cluster. So now we've actually changed the clusters to be like this and like this. And that's identical to the clusters found in the previous problem. And so we actually already know that these will converge. And so the answer is no. This is not the original clusters cannot be a converged answer, because if you run one more iteration of k-means, you'll get a new cluster. You get new clusters. Any questions?
I find the wording of this problem very confusing. I thought it was asking us to come up with an initialization of centers that would lead to a different convergence.
Yes, yeah. So because this, if you were to run one more iteration of k-means, and you couldn't get this, you can't get this cluster pattern, since you can't get that, it's not possible. So yeah, so I guess to answer your question, the original question, so it is asking if you can find initialization. And the answer is no, you cannot find an initialization. That will
You had 0, -1 as one center and 0, 2 as another center.
Okay, let's try it. So 0 and -1. You're saying right here?
No,
Here. Avenue 1.
yeah, x is 0, y is -1.
Okay, so you want right here?
Yeah, that's one center, and then 0, 2 is another center.
Okay, that's one center. And 0, 2. 0, 2 right here. Okay. Okay, so you're asking, will this come up with this same cluster pattern? Okay, so let's try it.
I mean, it's non-deterministic because the 4 going across it's a tie for those distances, right?
Yeah, so it is a tie. So that's true. So you could randomly assign it, or you could do any form of assignment. You'd have to make some sort of decision on how you would make that assignment to break those ties. That's true. But you still wouldn't get this cluster pattern. It's not possible. Because it wouldn't be the converged answer, because if you were to run one more iteration,
Okay.
you would get a different pattern.
Yeah.
Yeah.
So when we were trying to find the initial centers given these clusters, finding the centers first, that is the first step. But finding the centers and doing the reclustering, that's the first step.
So you're asking, what is the first step?
How do we determine the end of first iteration?
Yeah, so here, okay. So here we had they had given us clusters. So they had basically done, I think normally I would say, like, I guess what you do is you randomly initialize, right? That's how you start k-means. Then you assign points to those random initialized cluster centers. Then you recompute. So your algorithm, I guess, is, I'm just going to write in words, just random init, right? And then you have some sort of a loop, like while not converge, you assign points, and then you recompute centers. And then and you just keep doing that until you converge.
I have a follow-up question.
Mm-hmm.
Now, we learned that in k-means, the choice of clusters is heavily dependent on the initialization, right? Now,
Say that again, sorry.
for k-means clustering,
Uh-huh.
the choice of the center, the final centers and the final clusters are heavily dependent on the initialization.
Yeah, they're
Right.
dependent on
So
initialization.
now when we are solving such a problem, it is possible that, okay, we now have ended up with two different clusters that are not same as the original clusters.
Uh-huh.
Now it could be possible that we could come up with some other centers, some other initialization, which could potentially give us this solution.
You're asking, is this solution possible as a converged
Right.
solution?
It could be a thought process that goes on when we're solving such a problem in the exam. So how do we...
Yeah, so the way I approach this is the key is convergence here, right? So for a k-means solution to have converged, if you were to run it for one more iteration, you would get the same answer.
But that will be only a local optimum, right? You will never get a global optimum. Unless you know
And
that there is
that would be with a local optima.
Right.
And so it will converge to a local optima.
So how do
K-means
we-
always converges to a
how
local
do we know
optima.
that there isn't another local optima where this is a solution?
Because you run this, so since you can run this for one more iteration, so you can ask, let's assume that we do have these clusters. That's what we did. We assumed that we had these clusters. So we compute the centers given those clusters, and then we ask, do we still have those same clusters? Yeah. So you just check if it converged. Okay, any more questions about k-means? Okay. Okay. Now PCA. So I'll give you a minute and then go through this one. Okay. All right, so here we are, so consider the following two plots of data. Draw arrows from the mean of the data to note the direction and relative magnitudes of the principal components. Okay, so start with the left plot. And we have the mean of the data, which is probably somewhere around there. And PCA, principal component analysis, the principal components that you will get out of that will be aligned, will be ordered in terms of the amount of variance that each axis explains. Or in other words, if you were to project the data onto that axis, the first principal component would maximize the variance that you would get. The second one would maximize the residual variance that you would get. So the most variance occurs in this direction. So we get a big arrow in that direction. And then the next axis will be orthogonal to that and will explain less variance. And so it'll be a smaller component. This is orthogonal. It doesn't look orthogonal, but it is. And same over here. The mean is probably somewhere right here. And you have a lot of variance in this direction, a little bit less in this direction. And so, again, you get big there and less big going upward. Any questions?
How do you decide the direction of the arrow, not the second case? How do you decide if the second arrow is pointing upwards or down?
Oh, it doesn't matter. Yeah. It can go either way. Any other questions? Yeah.
So if you have 2D data, then you have at most two principal components.
Right.
How do we prove that there is no other principal component that gives us the maximum variance?
How do you prove that there's no other principal component that explains more variance? I'm not sure how you'd.
Not necessarily math, but then based on the diagram.
Yeah, so this is more of a conceptual question. I don't. So proving that, I don't know how you would prove that there's another one that has more variance, but just like eyeballing it. I mean, you could use a ruler, I guess, and measure or something, and see that it doesn't. You just like find the direction. So like you're centered at this point, and you could, I guess, you could go around in a circle and find the side that would give you the largest circle, it's the largest radius from that center. Does that make sense? So I mean, you're centered here. Let's say I went in this direction, and if I were trying to, for the second principal component, yeah, I don't know if I'm going to be able to answer this well online, but maybe afterwards we can talk about it. Okay.
It's just a closed form solution.
For
Do like SVD.
you need SCV, sure, but on a conceptual question like this, I don't know how you would prove it other than just looking at it. Yeah. The magnitude, I mean, it's somewhat arbitrary. You just, in this question, as a TA, we would just grade you to make sure that you have roughly the correct relation between the two magnitudes. So just knowing that this principal component should be larger because it's explaining, because it tells you to make their magnitude, actually it doesn't tell you what to make the magnitude relative to, but this is the magnitude of the amount of variance explained, I guess, is what it means here by relative magnitude. Yeah.
When we had this question on a real exam, we were just looking to make sure that you had the first one bigger than the second one.
Yeah. Because I guess if you're thinking of the eigenvectors, for example, those are all have a magnitude of 1. But this is also I guess, looking at the eigenvalues too. That's what it wants for the magnitude, is the eigenvalues. Yeah. Can you say that again? Sorry, the direction of the...
Like, so you also like pick the direction with the first principle, like go backwards.
To go this way? Yep, you could. Yeah. The PCs are only unique up to a sign change. So. Okay. All right. This is maybe for sake of time. Should we skip this one? Yeah. Let's skip this one. Okay. We're gonna go on to an SVM question. I'm not going to give too much time on this one. So this one is just asking, so if you have separable points, you have separable classes, will SVM, the margin that you get from SVM, be larger, greater than or equal to the margin from the perceptron? That is true. So SVM is the maximum margin classifier. So it will, this is the SVM margin. It will try to maximize the distance between these 2 points, this point and this point. This is SVM. Perceptron, you have no guarantee. It could be any of these, anything that separates the two classes. Okay. All right, next question. Yeah. So I'll give you a minute for this one. Okay. All right, so we have a soft margin SVM, which I believe is on the homework. And so you guys are all thinking about this right now. So, all right, so what happens as we adjust the parameter C? specifically as we increase C. So I just came up with a little example that hopefully gives some intuition about this. So let's say we have some sort of axes, and we have some data. Two classes. All right, so far so good. We're linearly separable. Now I'm going to put a point right there. And I'm also going to add, just to help us develop some intuition about this, I'm going to add a point right here, and I'm going to add a point right here. Okay, so let's say we set C to be very small. So in that case, the error penalty has a very small effect on our cost function. And we can set the error to be arbitrarily large without having a big impact on our cost function. And so our algorithm's goal in life will be to make that margin as big as possible without caring about how many points are misclassified. And so what it will do, this is going to be the C small axis. It will maximize the margin between these 2 points right here and have a bunch of points misclassified. So C equals small. Yes, I can do that. Okay, any questions there? So let's C is small. Now as C gets bigger, so this is a really big, something we want to think about here is when the term margin might be a little bit confusing when we're talking about a soft margin, but you can think of it more rather than trying to. So in the linear separable case is really clear. Like you had a distance between the closest points between the two classes. In a non-linearly separable case, we are basically thinking of the margin as sort of having more points correctly classified on either side and having the greatest distance between those correctly classified points. So in this case, with that sort of hand-wavy definition of margin, this has a very small margin because a lot of these points are misclassified. And so as we increase C, we get a greater penalty for all these misclassified points, and so we're going to work harder to try and classify them correctly, and so we might get something like this, that maybe it misclassifies this one and gets a penalty for that, but it's able to classify all these other ones correctly. So C equals large. And so between these main groups of points, there is a the margin, I guess, would be sort of defined right here, and then that's where the penalty would start, and then you would start. This was the only point that would be penalized. So sorry, that was a little bit hand-wavy in terms of definition of margin. Are there any questions? When C is small. Maybe. Sarah? So drawing the margin when C is small. So one thing that I'm not sure about in this question is the definition of margin when it's not linearly separable. So maybe.
I'm not sure I understand the drawing.
So the idea of, so we have C is small,
Yep.
so it would ignore all these points and just try to make W as 1 over W as large as possible.
Right. So I think that all these ones it's not caring about would be like inside the margin. So the margins would be like here.
Yeah. I think so the answer to this question is that it decreases or remains the same as the margin size.
Mm-hmm.
I think on the actual exam, so this is I think from a mock exam that we handed out to you guys. I think for the actual exam, we'll have a better question than this. But my hope is though that this gives you some intuition for what happens as you change C, and like how C here, when it's small, it will ignore classification penalties in order to sort of maximize the distance between any of the points. When C is large, it will really pay attention to misclassified points, and so it will try to classify as many points correctly as possible. So any questions about that intuition?
I understand the intuition behind small and large values. What if it becomes 0 or infinity? Then suddenly it doesn't matter anymore, right? Because sort of you can draw any line and have no penalty or infinite penalty. So how then does the objective function work?
Yeah, this sounds a lot like a question from the homework.
Confusing because if you ask if C becomes smaller, then the intuition holds. But if it becomes 0, then suddenly it changes, right? Like, is it the same intuition that you want us to apply?
Yeah, so
I think the intuition still holds.
Yeah, I think the intuition still holds.
Also, the homework problem says as C approaches 0 or infinity, not like becomes it. If you're getting after the homework problem.
Yeah. In this case, if you had infinite penalty on this point, you might encounter some issues, right? But maybe we should move on to the next.
Yeah, I think we should. We only have like 10 minutes left,
Yeah.
so we should probably try to go on, and then if you have questions, you can ask after. But. The next question is just kind of an intuition question on AdaBoost. Oh, I forgot to bring paper up, but that's okay. So I'm just going to put these both laptop because I don't think I need to write down any of these answers. So after doing an iteration of training, AdaBoost will more heavily weight which data points when it goes before it gets ready to train the next weak learner. Just an intuitive answer, not mathematical. Does anyone have an idea which data points is AdaBoost going to weight more heavily? Yeah. Yeah, exactly. So the ones that were misclassified in this iteration will get weighted more heavily. The follow-up question, what happens to the weights of the other data points, the ones that were correctly classified? They don't get weighted more heavily, but what do they yeah, they get weighted. Their weights decrease. Exactly. Good. That's all I have for little AdaBoost questions here. But are there questions on that? Okay, cool. So the next question is, this is a question about reinforcement learning. This is a select all that apply which of these are true of Q-learning. So think about each of these for a second, and then we'll go through each one, whether we think it's true or false. Okay, so for A, works best with smaller state spaces. Who thinks that's true? Who thinks that's false? Okay, only some people voted. It's actually true. That's why with a larger state space, you need to start doing things like deep reinforcement learning, which we touched on but didn't cover hugely in class this semester. But so in Q learning, you do need to be able to keep your Q values in memory. So it's best to have a smaller state space. I mean, you can use what might look kind of large to a human and still be able to do Q learning, but you can't do, an infinite state space or, something like learning to play a complicated video game without doing more deep reinforcement learning. What about B, keeps a log of all individual actions taken by the agent? Who thinks that's true? Who thinks that's false? Okay, good. Yeah, it looks like most of you got that. Yeah, that's not true. That's kind of part of the point of Q learning, is that you don't need to keep track of every action that you've taken. And C requires the agent to know the reward for every action. Who thinks that's true? A couple people. Who thinks that's false? Yeah, so that's false. The agent will get the reward from the environment each time it takes an action, and then can update its Q values. And D, models learning behavior in animals. Who thinks that's true? Who thinks that's false? Yeah, so that's true. It's similar. It's like a basic psychology idea of animals, learn tricks by getting a reward, or like a Pavlov's dog type of thing. Or, you can teach your dog not to do something by punishing it. So negative reward. Cool. Any questions on that one? Okay. Pack learning. So this is a two-part question. What is the full name of pack learning? E.g., what does pack stand for? And what is the correspondence between epsilon, delta, and this name? So does anyone remember what pack stands for? I think I heard a few people say it. Probably approximately correct. Yeah. And does anyone remember what's the correspondence between epsilon, delta, and that name of probably approximately correct? Or have an intuition of? I don't know if we said it specifically in class, but yep.
1 minus epsilon is so part probably, and 1 minus sigma is approximately.
So this is delta, and I think that you have that the other way, actually. So it's that it will probably within 1 minus delta, right, be approximately within epsilon, or 1 minus epsilon, correct, right? So I think I actually said it backwards in this morning's recitation, so hopefully I said it the right way this time. But yeah, that's, this is from, I think, the 10601B midterm that you have on Canvas, and the solutions are there as well. So, cool. Any questions about that one? Oh, this one would be good to draw. Okay, so this is a question on VC dimension. Since we did that, I think PAC we did just before midterm, but we stuck that on here anyway. And VC, I think we did just after the midterm. But So our hypothesis space is going to be rectangles, which means they're axis aligned rectangles. And then, so like, can you see? So a rectangle would be like that. And the points inside the rectangle are positive and those outside are negative. So can we shatter 3 points with rectangles? Yes. Yeah, for any labeling of 3 points, we can find a rectangle that, so if there's just one positive one, we can put a rectangle around it. If there's 2, we can put a rectangle around those 2. If all 3, we can put a rectangle around all 3. If, yep. You could still, yeah, but to be shatterable, it means there needs to be some 3 points that you can, that for any labeling of them, you can you can do it with your hypothesis space. So yeah, I do see what you're saying, that if you had like plus, minus, plus, you wouldn't be able to get a rectangle. But there is some way of doing 3 points that you can put any labeling and get a rectangle. Yeah, if they're all negative, you just put the rectangle somewhere else. What about 4 points? Can we shatter 4 points with rectangles?
When it's 3 points and like there's a positive and a negative in between and a positive at the bottom, how can you separate that with one rectangle?
You can't, but the point is that, so like if these were all in a line, that wouldn't work, but it's, to be shatterable, it means there exists 3 points that any way I label them, I can find a hypothesis in my hypothesis space that can do it. So if they were all in a vertical line, then no, you wouldn't be able to do it. But these 3 points, for example, I can put any labeling on and correctly classify with a rectangle. Okay, what about 4 points? Can we shatter 4 points with rectangles? No. I don't know. So if you have 4 points and if you have 4 points in some, like, it doesn't matter how they're created, there's going to be a way that you can label them. Like, for example, this one plus, minus, minus, like an XOR. I can't shatter that. I can't put a rectangle on it. Yep. No, but a rectangle is axis aligned.